So last time we proved this theorem 7.1. We looked at the proof of this. So this is the second polynomial congruences chapter. So we're working towards our kind of description of an algorithm for a general approach to solving polynomial congruences. And our first result that we built up is this nice result due to Lagrange, which places an upper bound on the number of solutions that a polynomial congruence might have when the modulus is just a single prime, when you're working modulo some prime p. This result tells us that as long as the polynomial is genuinely of degree n, so that means its leading coefficient an would be non-zero modulo p, i.e. not divisible by p. So when you look at the polynomial modulo p, it does genuinely look to have degree n. If that's the case, then that number n, the degree of the polynomial, is an upper bound on the number of solutions that the congruence might have. So we proved that last time. Any queries on the proof or questions about it? So, okay, now it was quite a substantial argument. It was a proof by induction. So we inducted on the degree of the polynomial, starting with linear polynomials of degree 1. Then we did an induction on that to go from degree 1 to degree 2 to degree 3 and so on. But most of the work in the proof by induction is proving the induction step, and that required a proof by contradiction, which we constructed. Okay. So we talked about that last week, and then, well, there's just some corollary of it here. So a corollary is like a short, immediate result that you get following, having proved a major result. So this corollary kind of looks at the result we've just proved in the opposite direction. So it says if you do have a polynomial of degree n, and if it does turn out that it has more than n solutions modulo some prime p, see, we just proved before that it shouldn't have. That as long as it was genuinely of degree n, n would be an upper bound on the number of solutions. So if you do come across a polynomial, like just consider it as a symbolic sum polynomial has degree n, where the highest power of x is n. If it does have more than n solutions modulo p, really that means actually everything is going to be a solution. It follows then that all the coefficients of f will be congruent to 0 modulo p. So really, f is just the zero polynomial when considered modulo p. All its coefficients look like 0 modulo p. So f is just the map sending every congruence class to 0. So it's going to be solved by everything. And so this is a proof by contradiction. So it's quite short. So we suppose on the so it's proof by contradiction. So we immediately assume that what we're trying to prove is false, and then show that that leads to a contradiction. So we suppose, on the contrary, that there is some coefficient that is not divisible by p. So one of these a's, see that the result claims that all the ai are divisible by p. So we say, well, suppose that's false. So if it's false, that means at least one of them is not divisible by p, and we let a capital N be the one with the largest index, I. Okay. So an is the kind of highest degree coefficient of the polynomial, which is not divisible by p. So this index n is less than or equal to n. Little n, remember, is the total degree of the symbolic polynomial. So a capital N is the first. When you go down through the degrees, the first coefficient you find that is not divisible by p. But then what we're looking at is this is the polynomial when considered modulo p. Because when you consider it modulo p, all the higher degree terms, you don't have to include those, because by arrangement and by definition of this index capital N, all the other higher degree terms are congruent to 0 modulo p. So the polynomial reduces to this. So we got this polynomial here, sum from I equals 0 to capital N. And this polynomial has definitely more than capital N solutions. Assuming in the conditions in the corollary that our f has more than little n solutions. Little n is larger than, is at least as big as capital N. But this polynomial here has more than capital N solutions. But then it's contradicting Lagrange's theorem. Okay? Because Lagrange's theorem says that any polynomial like this, of degree, well, this one has degree capital N, it has at most capital N solutions. But here we seem to have constructed one which has more than capital N solutions. So that's a contradiction. So our assumption led to a contradiction. This assumption we made at the start led to a contradiction. So there is no coefficient that is not divisible by p of the original point. So therefore they are all divisible by p. That's just another way of looking at Lagrange's theorem. Now, what we haven't done there is described any particular algorithm for finding these solutions. And it can be hard to do that. So in general, finding solutions to polynomial congruences modulo p, it can require a combination of approaches. We can attempt to symbolically or algebraically factorize the original polynomial into factors with integer coefficients. We can apply techniques like completing the square. We can test each congruence class in turn if the modulus is small. But at least that theorem, Lagrange's theorem, it gives us an upper bound on the number of solutions that we can expect. Okay. So now we're going to go on to the next section. And I don't have spare paper, so I'm going to work that forward. So remember, what we're moving towards is we're moving towards a situation where we're trying to solve, well, I don't have it written down there, but we're trying to solve the general problem of f of x being congruent to 0 modulo some general modulus n. Okay. And the way we're going to approach this general problem is we're going to make use of the prime factorization of n. Okay. So the fundamental theorem of arithmetic tells us that every integer n can be factorized like this. Okay. And using properties of congruence, this congruence being satisfied is equivalent to we can break this original congruence up into a set of congruences, one congruence for each prime appearing in the factorization of n. Okay? So this single congruence being satisfied modulo n is equivalent to this set of congruences all being simultaneously satisfied. Okay? So we can break down our single congruence at the start into a set of congruences where each one is modulo a prime to a certain power taken from the prime factorization of n. Okay? And then the general method is going to be to solve this simultaneous system this will give us to obtain solutions. When you solve the simultaneous system, you'll obtain a set of solutions, x being congruent to bi modulo pi to the ai. Where I goes from 1 to r, we'll have a set of solutions like this. Okay. And these then can be lifted using the Chinese remainder theorem, which we proved a couple of lectures ago. See, because these different powers of primes, because the primes are different, P1, P2, P3, etc., these powers of primes are going to be all co-prime to one another. So the Chinese remainder theorem is going to apply. So this will give us a single congruence class, let's call it x congruent to beta modulo n. So this will give us a solution to the original problem we were focused on. And each set of choices bi because you might have a whole bunch of solutions to the first congruence when I is equal to 1, modulo P1 to the A1. You might have a whole bunch of solutions to the second congruence, f of x congruent to 0 modulo P2 to the A2. And putting those together in sets, so each set of choices of bi, choosing one bi for each value of I, each choice like that will be lifted by the Chinese remainder theorem to a unique congruence class, x congruent to beta modulo n. This is how we obtain all the solutions to our original congruence. Okay. So that reduces the task at the moment is how to solve this step here. Okay? And that's what we're moving into now. Okay? How to obtain solutions to a polynomial congruence modulo a power of a single prime. Okay? This is what we turn to now. Now we're going to try and solve this type of problem. On the following page, there's an algorithm presented, and it's a kind of a lifting procedure. So we're trying to solve f of x congruent to 0 modulo prime to some power. So what we do is we start, so we're going to describe this lifting procedure, which takes solutions to the congruence modulo p to the k minus 1, and it lifts them to solutions to the congruence modulo p to the k. So if you have solutions to a smaller power of the prime, you can lift them up to the next power. So we're going to start at the ground level and first solve the congruence modulo the prime itself. Find all the solutions to that. And then lift them to solutions modulo p squared. Then lift them to solutions modulo p cubed. And keep going until we reach the desired power of the prime, p to the a, whatever that is. Okay? Now the method for lifting is described here in this theorem. It's a kind of a description of an algorithm. We're not going to prove it at the moment. I might go through arguments for justifying it later on. But I think for the moment we're just going to jump in and work an example, okay, and see the various parts. Now I think that's about the whole thing on the screen just in one shot, but you can see it in the notes beside you. So this describes the procedure. So we assume that we've got a solution R to f of x congruent 0 modulo p to the a minus 1. And what this procedure is going to do is produce solutions, if they exist, which are associated to that R, but which are solutions of f of x congruent to 0 modulo p to the a, to the next higher power of p. Okay. Now, I won't kind of describe all the parts of it in general. I think we'll start working through an example, and we'll point to the various parts of that result as we go. It's kind of one of these things that's best to see being set out with the aid of an example to see where the various parts are taking place. I think I'll just work on the whiteboard. Okay, so we're going to look at that example after example 7.1. So this is x squared polynomial f of x is x squared plus 3x minus 16 congruent to 0 modulo 81. Now 81, of course, is a power of a prime. It's 3 to the power of 4. 9 times 9. So we start off. So first we're going to find the solutions to the bottom level, which is x squared plus 3x minus 16 congruent to 0 modulo, not 3 to the power of 4, but 3 to the power of 1. So just modulo 3. Now, how hard is it going to be to solve something modulo 3? Well, we can do it pretty darn quick, because there's only modulo 3, there's only 3 possibilities, 0, 1, or 2. They're the only objects around. Congruence class of 0, congruence class of 1, congruence class of 2. So you only have to test 3 cases. You could just go ahead and test the 3 cases, but you can even make it simpler still. You see, if you're working modulo 3, this polynomial is the same. You see, really if you're working modulo 3, what does this coefficient 3? What's a better description of 3? Well, modulo 3, that's a 0 coefficient. So there isn't an x term in it. And what is 16 modulo 3? 16 modulo 3 is 1. So really, this is x squared minus 1 being congruent to 0 modulo 3. And this has solutions. This has 2 solutions. X squared has to be congruent to 1. So effectively, x can be plus or minus 1 modulo 3. So this has 2 solutions. X being congruent to 1 or 2 modulo 3. I mean, you can test that out in the original case. If you put in x equals 2, you get 4 plus 12 to 16. 16 minus 16 is 0. So definitely congruent to 0 modulo 3. If you put in 1, you get 1 plus 3, which is 4. 4 minus 16 is minus 12. And minus 12 is indeed congruent to 0 modulo 3. Okay, so we've got 2 solutions, 1 and 2 modulo 3 to f of x being congruent to 0 modulo 3. So now we're going to start making use of this result here. So this r that's mentioned here, this r, well, to take the place of r, we can use 1 or 2. Okay, yeah.
You know when we had x squared minus 1, that minus 1 was taken from 16 modulo 3.
Yeah.
Do we take 16 or minus 16?
Well, I kind of left the minus sign there, and I just looked at 16. So I asked myself, what is 16 congruent to modulo 3?
Why not consider the minus sign?
Well, I did, but I just left it there. So you could either use the fact here that 16 is congruent to 1 modulo 3, or you could use the fact that minus 16 is congruent to minus 1, which is 2 modulo 3. Either way, it's the same. It's the same thing. So in my mind, I thought the simplest thing to do is just replace 16 with 1 and keep the minus sign. So now what we're going to do is we're going to let r equals 1. So we're going to take the first of our solutions. We've got 2 solutions to start lifting up, but we're going to just choose the first one. So we let r equals 1. So now we're in the situation of this theorem. We've got our polynomial congruence, original f of x, congruent to 0 modulo 3. We've got a solution of it, r equals 1. So now we're going to lift it up to the next part. Okay. So we let r equals 1, and we're dealing with a equals 2. So we've just found r equals 1 is a solution of the congruence modulo 3 to the power of 2 minus 1. Modulo 3. We're now going to try and lift it to modulo p squared. So the first thing that the theorem says is it's based on these two bullet points here. Okay, so we've got a condition to check, and the condition is checked on is based on the derivative of the polynomial. So this f prime here is the derivative of the polynomial. So we're going to calculate the derivative of the original polynomial and evaluate it at r. And we'll either get 0 modulo p or we'll get non-zero modulo. And depending on what we get, leads us into what we do then. If we get something non-zero modulo p, the result tells us that our solution r is going to lift uniquely to a unique solution s modulo p squared for the polynomial. That's the kind of nicest or simplest situation where your one solution to the thing modulo 3 corresponds to one solution to the polynomial modulo p squared. If the test works out the other way, if we do get 0 modulo 3 when we test f prime, then one of two things can happen. Either, this is another test to consider, you then consider the value f of r modulo p to the a, and again you either get something 0 or non-zero. If you get something non-zero, that's kind of nice in a way, because you kind of reach a dead end. Your solution r to the previous case, modulo p to the a minus 1, is not going to correspond to a solution to the higher power. But if you get something congruent to 0, then it will correspond, but it corresponds to multiple solutions to the next higher power. But this is the case where your single solution, modulo p to the a minus 1, is going to split into p different solutions, modulo the next higher power. Okay? So the first thing we've got to do is calculate the derivative of f and assess this condition here, which is in these first two bullet points. So we find f prime. F prime of x, just the straight derivative of the first one. This is 2x plus 3. Okay. And we check f prime at r. So this is f prime at 1. So you evaluate this polynomial at 1, and you get 5. And we have to assess that 5, assess it modulo p. Well, 5 is certainly not congruent to 0 modulo 3. Okay. It's congruent to 2 modulo 3. Okay. So we're definitely in this first case. Okay. We've got our solution r. When evaluated that the derivative is non-zero modulo 3. So our r will lift to a unique solution. Our r will lift. So lift means it's going to come up from a solution modulo 3 up to a solution modulo 9, modulo 3 squared, will lift to a unique solution. Unique solution S. And the solution is given to us here. So S is going to be equal to R. R is 1 plus t times p to the a minus 1. So this is t times 3. Our p is 3. Our a minus 1 at this stage is 1. So this is what S is going to be, but this is depending on t. So our t is the solution to t comes from the solution of this linear polynomial here, which is t times f prime of r, so that's 5 times t, plus f of r divided, this is going to be f of r divided by 3. Which was, see, f of r was minus 12. So I need to divide that by 3. And this is congruent to 0 modulo p, which is 3. So i.e. it's 5t minus 4 being congruent to 0 modulo 3. But if you're working modulo 3, 5 is 2, 4 is 1, so it's minus 2t congruent to 0 modulo 3. So this is my 2t has to be congruent to 1 modulo 3. So my t is congruent to 1. Sorry, t is congruent to 2 modulo 3. It's 2 times 2 is 4. It's congruent to 1 modulo 3. So my t comes out at 2. So we get s is equal to 1 plus 2 times 3. 1 plus 6, so we get s is equal to 7. We're talking about the congruence class of 7 modulo 3 squared. So we're talking about 7 modulo 9. So the claim here is that 7 is a solution to f of x congruent to 0 modulo 9. So we can check that. We put in 7, we get 49 plus 21. 49 plus 21 is 70. Yeah. Sorry. Yeah, 49 plus 21, 70. Minus 16 is 54. Is 54 congruent to 0 modulo 9? Yeah. 54 is a multiple of 6 times 9. Okay. So it checks out. Yeah.
You know, 5t minus 4 to the next line. A bit down. Yeah, that one to the next line.
Yeah. What did I do there? Well, so, okay, so that would be completely wrong if this was an equation.
Oh, modulo 3.
Modulo 3. What is 5 modulo 3? It's 2. What is 4 modulo 3? It's 1.
What about the bottom line? So you know, just a bit lower. That one to the next one.
Well, this was, I just picked out the solution from my mind.
But isn't it half? You can't have half.
No.
Oh, right.
We're dealing with integers here. We're dealing with congruence classes modulo 3. Now, there's not that many. There's only three possibilities for t: 0, 1, or 2. So I just quickly went through them in my mind. Which one, 0, 1, or 2, satisfies 2t congruent to 1?
Oh, yeah.
While it's t equal to 2. Yeah.
Okay, sure. Okay, like this.
You can kind of say it's t congruent to 1/2. As long as you understand what the
rules are.
What the appropriate interpretation of a half is in this context. If a half is 1 times the multiplicative inverse of 2 modulo 3. That's how you get you have to multiply both sides, or you have to divide both sides by 2, which is multiplying both sides by the multiplicative inverse of 2. And what is the multiplicative inverse of 2 modulo 3? What number do you multiply by 2 to get back to 1 modulo 3?
2.
It's 2.
Yeah.
So this is just 1 times 2.
Okay.
So as long as you interpret it correctly, you're not wrong when you say t equals a half.
Okay.
But you say, well, what you mean by a half is 1 multiplied by the multiplicative inverse of 2.
Sure.
Okay. Now we are wanting solutions modulo 81. Here we've got a single solution modulo 9. So we need to go back into this result again.
So on the left-hand side, just let r equal 1 and a equal 2. Why did you pick the figures?
Well, r is just one of these solutions.
So it doesn't matter which one.
Yeah, I mean, we could have started at 2. I chose to start at 1.
So it just chose r to be 2, a must be 1.
No, a here was the degree. The a is this power on the prime. I wanted to obtain a solution modulo 3 squared. So this a equals 2 is this square up here I was heading towards. So if you look at the way the theorem is quoted, that you're starting off with the solution modulo p to the a minus minus 1.
Okay,
So
so
starting off with a solution modulo 3, so a minus 1 is 1, this index up here is 1, so a is 2.
sure.
So now we need to go back into the theorem again. So now we reapply 7.1, theorem 7.1, this time with r equals 7. So now I'm continuing on and seeing if this solution is going to lift, and a equals 3. Okay, so I've got a solution to f of x congruent to 0 modulo 3 squared, and I want a solution to the higher power. Okay, so we first have to check this condition on the bullet point. I have to evaluate the derivative at 7. Derivative I already have, it's 2x plus 3. Evaluate at 7 is 14 plus 3, which is 17. And that's certainly not congruent to 0 modulo 3. See, that's the condition to check whether it's not or it is congruent to 0 modulo 3. So I'm back into this first case again. So this is going to lift uniquely. So R, now meaning 7, R will lift uniquely to S, and the S is going to be 7 plus, this time, 7 plus 9 times t, okay, because this p to the a minus 1 is now 3 squared, where t solves, what is my t going to solve? T is going to solve f prime of r, which is 17. 17 times t. I need f of r. F of r I worked out before, wasn't it? It was 54. And that gets divided by p to the a minus 1, which is, a is now 3, so p to the a minus 1 is 9, 3 squared. And this is congruent to 0 modulo 3. So what's this? 17 is 2 modulo 3. Again, this is 2t plus 6. What is 6 modulo 3? 0. So it's 2t congruent to 0 modulo 3. What's the solution to that? What you multiply by 2 to get 0? Yeah, 3, or even simpler?
2. Oh, you mean actually? 3.
Somebody whispered it there. Who was it? 0. Yeah. What do you multiply by 2 to get 0? What do you multiply by 0? Which is also 3, because you're working modulo 3. But we choose as t. You see, the t has to be the standard representative. So in the range from 0 up to, but not including p. Yeah, so you wouldn't quote t as 3 here, you quote it as 0. So in other words, we're left, so our S, our new solution is going to be 7 plus 9 times 0, but still 7. So we get the solution 7, x congruent to 7, but we're now talking modulo 3 cubed, 27, to f of x being congruent to 0 modulo 27. Just check that it is. Is 7 a solution modulo 27? So what is f of 7? Well, we worked that out a while ago. It was 54. Is 54 congruent to 0 modulo 27? Yeah. 54 is 2 times 27. So that checks out. So you see what's happening here. We started modulo 3. We're now up to modulo 27. We've got a solution 7. So now we need to go back into it once again. And now apply theorem 7.1 with r equal to my current solution I have, which is 7, and a equals 4. So now we're finally going to get to modulo 81. So my f prime of 7 is still as it was before 17, which is still not congruent to 0, modulo 3. So again, we're going to get unique lifting. So R lifts, R, which is now 7, R lifts uniquely to S, solution S, which is 7, but this time plus 27 times T. This is my S equals R plus T times P to the A minus 1. So it's 7 plus 27 times T, where T is the unique solution. T is the solution to this linear congruence we get again, which is yeah, 7. No. F prime of R. F prime of R is 17. 17 times T plus F of R, which is 54 over your 27, congruent to 0 modulo. So this is still 2T, and 54 is 2 divided by 7, so I'm looking for this. So I'm looking for 2T being congruent to minus 2 modulo 3. So you're kind of, you know, your A-level mind tells you 2 times T equals minus 2, T equals minus 1, which is correct. But we're working modulo 3, so we should quote that as minus 1 modulo 3. Not 1, but 2. 2 is the minus 1 is congruent to 2 modulo 3. The distance between minus 1 and 2 is 3, the multiple of 3. So T is congruent to minus 1, which is congruent to 2 modulo 3. So it's that 2 that I take. So that 2 goes into here, which gives S and it's going to be 7 plus 2 times, so 7 plus 54, so 61. So we've got a congruence class of 61 now. This is representing modulo 81, 3 to the power of 4. This is our solution we've got to f of x being congruent to 0, modulo 81. So finally we reach the top. We started at modulo 3, jumped to modulo 9, modulo 27, modulo 54, and now, 9, 27, and then one more, we got up to 81. But we're still kind of only halfway gone, because this is where the solution 1 lifted to. So this 1 became the 61. Well, you've got this other candidate there. You have to kind of go through the whole process again, starting with r equals 2, and lift that in stages up through the powers of 3 to get another solution. To just quickly confirm that we're working correctly. So Sage command solve mod, so this is x squared 3x minus 16. And it's modulo 81. It's a 17 and 61. So we found one of the solutions, 61. So this other solution 2, if you work correctly, should come out as the congruence class of 17 modulo 81. These are congruence classes modulo 81, because that's the modulus of the original problem.